All right, so in this lecture, I want to go over what an operating system is and why they're useful. So, you may remember from 200 or prior classes, when we're programming a microcontroller, we'll define a single function, int main. When the microcontroller boots up, that's exactly what the microcontroller will run and nothing else, right? We'll declare a resource like an LED and then do this forever. So while this statement is true and one is always true, turn the LED on, set it to 1, wait 10th of a second, turn it back off, and then wait for a 10th of a second. And once you get down to line 10, you're of course going to drop right back up to line 6 and continue again and again and on and forever. All right, and that's perfect. That's going to blink a light for us. So how does this actually get onto the microcontroller itself, though? This is text typed into a code editor. What we need to do is put it through a program called a compiler, which is going to use the rules of the C programming language, along with the knowledge of the target processor, how its instructions and transistors are laid out, and then produce a set of ones and zeros that represent this program. So this set of ones and zeros is the compiled, we'll call it a binary. And that is specific to the target processor. Once it's loaded on here, that's the only thing this processor will do. Okay, so I want to just again emphasize the fact that compiled code is specific to a target processor, a hardware type. And in this model, the only thing the processor does is run my while one loop. So let's look at this program in a little bit more depth here. If I were to run this program for several minutes, I would execute line 7, line 8, line 9, line 10, line 7, 8, 9, 10 again and again and again. So each one of these lines would be executed the same number of times. But how long will I spend executing line 7 versus, for example, line 8? So it turns out the microcontroller, this LPC 7068, has a clock around a few megahertz. So that means every millionth of a second it can execute a new instruction. So line 7 takes roughly a millionth of a second. And how long does line 8 take? Right? Well, it takes a tenth of a second. So if we were to plot out, say, where our microcontroller is in terms of execution, the vast majority of the time it would be sitting here at line 8 and at line 10. All right? And there's really no good work being done in line 8 and 10. We're just stalling until we want to do something else interesting, which is line 7 and 9. And right, I can execute 100,000 of these line 7s in the same time it takes me to do this wait. So I could do a program with 100,000 more instructions and do that entire thing if I was able to kind of squeeze it in this wait section here. It just again to drive home the point about how fast these machines are. Let me show you just the circuit board of this Raspberry Pi, which is not strictly a microcontroller, but it's in the same sort of family. So let's switch over to my document camera. And this, I'll show you here just for a size. This is like the size of a credit card here, and it's using something similar to a several previous generations of cell phone, maybe like a early 2000s cell phone. So as I look at it under this kind of bit of a magnification here, the actual processor, the thing that's doing all the work, is underneath this aluminum heat shield or heat sink. And the reason we need this is because every time the computer, in this case the microprocessor, executes an instruction, some transistors flip state from on to off, from high to low. And there are so many of them, and they all are switching so fast they actually produce enough heat to really melt and damage this board, unless you were able to extract that heat with these aluminum fins. Thank you, buddy. And so that I think is phenomenal. I mean, these transistors, which are much smaller than the human eye can see, are actually, there's so many of them working in tandem so quickly they'll produce enough heat to literally cook an egg if you were to get a very small egg there. But let's look just for now at the routing on this circuit board here. So the way these boards are made, you have a fiberglass plate, and then we're going to lay copper on top of it, and the copper is going to form wires that connect components to each other. So here are some capacitors and other passive devices all connected to this processor. And down below here you see we've got the video header if you wanted to add a screen to this device and HDMI pins. And as we look at the patterns of the wires connecting these devices, look how complex these paths are. I mean, what we really need, to connect point A to point B is just a straight line, right? And particularly here, look at this. I mean, I want to go from these two pins here to the processor, and for some reason I've taken a real circuitous route. Even worse up here. So why is that? Well, it turns out this processor is running at a gigahertz or thereabout, and that's like 1 billion instructions per second. At that speed, we actually have to worry about the propagation of the electromagnetic field through these wires, right? Basically the speed of light. And just to, you can really see this physically. So here is a set of pins that are all going to get a set of ones and zeros, and that's going to correspond to, a pixel value on a screen. And they need to be, generated by this processor and sent over to this header. So maybe you want to display red, and that's 1100111. I need to send those out from the processor, have them arrive here all at the same time. And look at this pin, right? If I was going to start a race, say this is a racetrack, and I was starting here, and my goal was to get to the processor, right? And I had a competitor perhaps up here, and the pin is just physically closer to the processor, right? This one is even closer still. If I were to say go at the same time and all of these runners would start racing straight as they could to the processor, this one would get there first, right? I mean, that's really the problem, right? The electrons essentially are going to arrive out of order. So I need to actually jog this wire to slow down, the propagation of the electric field down this wire. And that's totally due to the amazing speed of this microcontroller. Okay, so having a microcontroller sit here and do nothing for a tenth of a second, I mean, that's hundreds of thousands of execution cycles where we could be doing something useful. Great care has been taken to be able to use those execution cycles to do useful work, right? And you can see all the manners of these are called meanders. It's just something you need to do on high-speed circuit boards like this. So how can we take advantage of these very powerful processors to do more than just blink a light, right? And that's our goal. So let's go back to this slide here and say we have two programs now. Say, okay, I've convinced you that your microcontroller can do more than just blink a light on and off. You want to also have the microcontroller put out a 1 and a 0 over the serial line, right? So I'm using this print command here, 1, 0, and then waiting. Okay, so like we've discussed, there's no problem in terms of the microcontroller's capability to execute these and still have plenty of time left over for whatever else it wants to do. But our programming model is broken in that line 2 here, once I hit this, while 1, you're never going to hit the orange program. There's never any moment in here where it says, okay, here, do the orange thing, or vice versa. So how can we get both main 1 and main 2 running at the same time on a single processor? And that's where an operating system comes in. Okay, and I'm sorry here, this should really say program 1 plus 2. But just to, again, point out the amount of idle time in these programs based on these wait statements. Here I've just, and this is a cartoon so it's not to scale, but when the solid color indicates I'm doing useful work like turning on a pin or printing something over serial, and then the hashed region here indicates like idle time that I've told it to wait or not do anything. And so these all represent periods when the processor could be doing something else. And so what I can do is write a different program, like this gray one, and have it be an operating system. Have it schedule the execution of a chunk of program 2, and when program 2 is no longer doing useful work, switch over to program 1. When that's not doing useful work, switch back to program 2, and do this ping pong back and forth. So an operating system at the most fundamental level is a program, right, that can periodically switch the execution to different regions of code. And we'll do that using interrupts, which is not something we've talked about in these courses, but we'll get into when we discuss microcontrollers at a lower level. So this operating system is in the gray, and it is in charge of switching the processor between programs 1 and program 2. And the magic here is that the programmer of program 1 and the programmer of program 2 can still write their programs as before with a while 1 and think that they have total control over the microcontroller, right? They own every resource on this board, and the operating system is in charge of enforcing that abstraction that program 2 never is aware of or needs to care about program 1. And this is exactly how your laptop works. Now, your laptop might actually have more than one processor. Maybe it's got 4 cores or a few more, but you can certainly run a lot more programs than you have cores in your processor. For example, you could have multiple tabs open at the same time that you have Microsoft Word and PowerPoint all running at the same time, and your operating system, Windows in your case, is going to be switching just time slices of a little bit of web browsing, a little bit more YouTube, a little bit of PowerPoint, and as long as each program gets enough time to execute so that it's idle times are never overlapping each other, and then all's well, right? You don't notice the difference. The problem comes when you've asked the operating system to schedule too many programs at the same time, right? I insisted in program 1 that after a tenth of a second I would be doing something. If I get scheduled out and program 2 starts executing, and then program 3 and program 4 and program 5, it might be the case that by the time the operating system gets back to me, this is now quite a bit further down, and I've had to wait like 3 seconds, and then I get frustrated because it doesn't seem like I have a very responsive system. And maybe you've seen this when you have too much going on. All right, so what else can an operating system do in addition to allowing me to run more than one program at the same time? So that's its primary purpose, and we've said that's sandboxing programs, right? So that each program can be written as if it was just the only show in town. In addition to that, we want to be able to have shared access to common hardware resources so that multiple programs can listen for keyboard input, can write graphics to the screen, send network packets, to the over the network, Wi-Fi and Ethernet adapters. And we want to do that in some secure way, right? So that maybe one program can't actually see the graphic output of another, or that they can't interfere with each other's network traffic. And of course, we'd like to be able to start and stop programs. So really, when you turn on a computer, the operating system itself will boot. We'll often call that part of the operating system the kernel. And you really don't interact with the kernel at all. It's there in providing your sandbox and providing your shared access hardware resources, but it's really out of sight. Okay. The first thing you see is generally the first user level program, like your desktop environment, your window manager. And from there, that allows you to ask the operating system to add another program to its queue of execution. Then, of course, we'd also like to stop programs. So there are mechanisms for healthy programs to start and stop them through something like the desktop environment, or more aggressive, if a program's no longer responding, maybe you can hit Control-Delete and kill it at a lower level. Okay, so these three things we'll generally talk about in terms of, especially from the Linux side of things, is responsibilities for the kernel. But a real operating system that you're going to be familiar with is going to offer a lot more, right? In particular, desktop environment, the ability to log into it, maybe with multiple user accounts, some way to manage software updates as security patches come out or new programs are released. Nowadays, App Store is closely integrated in every major operating system, the ability to install certified applications easily, and of course a lot more. So some operating systems you may be familiar with. Windows is probably what you're using as you watch this. Android is by far the most widespread mobile operating system. iOS, of course, is Mac's version of it, of a mobile operating system. And then later in this course, we'll work a lot with Linux, and that is the dominant open source operating system. And to be fair, Android is actually based on Linux in many ways. So in Linux, we've got this, we call it Linux, but it's really two pieces, right? Linux formally is just these three, this kernel. And then there are multiple vendors that produce distributions on top of Linux that provide all of these other resources. So Ubuntu is probably the most popular one you may be familiar with. Red Hat is another. Debian, Raspbian is the operating system that runs on a Raspberry Pi. and etc. So we'll talk more about these particular operating systems further in the course, but these are their responsibilities. Okay, so the last thing I want to talk about here is a hard problem to get right. You know, the idea that we're going to have a single processor with one core be able to do multiple programs all at the same time and have each program think it has the processor to itself requires us to have very good kind of sandboxing capability here. In particular, we'll call this that the operating system is providing an abstraction of the hardware that each program is executing with the fiction and that it has the hardware to itself. If there are any leaks in this abstraction, then programs may be able to cross this boundary, that program 1 might be able to interfere somehow with program 2. Now, in our case of two programs blinking lights or sending ones and zeros to the screen, there's no big deal there, right? There's kind of a toy example. But you can imagine if one tab in your browser is your bank account and another is a game you downloaded, you certainly wouldn't want some buggy code in the game able to access the information shown in the browser with your banking information. And so here are some links to a recent vulnerability, really at quite a low level, and actually the hardware mechanisms in the modern Intel processors that allowed programs like program 2 to tamper with and manipulate details in program 1. So we may talk more about these going forward, but I think it's important to point out in an early stage here, especially as we create more and more abstractions and we start to be further and further from the hardware itself in terms of our thought processes and how our code works or runs. It's important to know that these boundaries are oftentimes the source of a lot of significant vulnerabilities or security problems. And so your ability to navigate these stacks and to understand what's happening at every level will help you understand these vulnerabilities and hopefully to mitigate them in your code, to know where you might be susceptible to somebody, either another process coming in, and how would that work, or as we talked about the internet, how do these abstractions of sockets and pipes, how can they be breached? And so we'll be talking about a lot of technology here. We'll be building a very complex layer of technologies, and the boundaries between each layer are oftentimes where these attack surfaces occur. All right, so that's it for this lecture, and next up we'll be talking about Python.